In the 20th century, one of the questions that has been bothering scientists for a long time was answered. This puzzle was a puzzle about the nature of the Sun. There is no other way to understand the nature of the Sun without looking at its interior. Especially the importance of its core is very important in this regard. First of all, if we focus on the dimensions of the Sun's core, the radius of the Sun's core is 139,000 kilometers and the temperature in its center is about 15 million degrees C, and the density in the center of the core is 150 tons per cubic meter. The reason for the very high temperature and very high density in the Sun's core is its weight. The weight of the Sun is 500 times heavier than all the planets in the solar system. The main reason why scientists are interested in the solar core is the process that takes place in the solar core. Here we are talking about that famous process, the thermonuclear reaction. The high temperature and high density of the Sun's core make it an ideal place for thermonuclear fusion. 99% of solar fusion power is produced within 24% of the Sun's radius. The diameter of the Sun is 1,392,000 kilometers, and the region that produces 99% of its heat is in the center of the Sun, which is about 340,000 kilometers in diameter. The main part of this region corresponds to the nuclear fraction and the region at the beginning of the radiation zone, that is, a thin layer at the boundary of the radiation zone with the nucleus. The energy source of the solar core is mainly formed due to the transformation of the hydrogen nucleus into helium nucleus as a result of fusion. There are two distinct reactions by which 4 hydrogen nuclei can ultimately lead to one helium nucleus. This reaction, a proton-proton chain reaction, is responsible for a large proportion of the solar energy and the CNO cycle. The core produces almost all of the Sun's heat through fusion, and the rest of the Sun is heated by heat escaping from the core. The main part of the fusion reaction in the Sun takes place at the outer boundary of the solar core and in the thin layer at the boundary of the radiation zone with the core. The thin layer at the boundary of this radiation zone with the core is called the outer core by some definitions. At a temperature of 7 million degrees C and a density of 10 grams per cubic centimeter, about 220,000 kilometers from the center of the Sun, fusion is almost zero. In the proton-proton chain reaction, which is the main cause of the fusion reaction of the Sun, 2 hydrogen nuclei initially fuse and become deuterium. During the collision of these 2 nuclei, heat and positrons and neutrinos are released from them. Then 1 hydrogen nucleus is added to the deuterium nucleus to form a tritium nucleus. During the collision between deuterium nucleus and hydrogen nucleus, heat and gamma rays are emitted from them. After that, 2 tritium nuclei fuse and become helium. When these 2 tritium nuclei collide, heat and 2 hydrogen nuclei are released. This reaction sequence is the most important in the solar core. The first reaction, the fusion of 2 hydrogen nuclei to form a deuterium nucleus, takes about 1 billion years, despite the extremely high temperature and enormous density of the Sun's core. The time required for subsequent reactions of deuterium and tritium is much shorter, only 4 seconds and 400 years. These later reactions occur through the nuclear force and are therefore faster. Here is the approximate time it takes for 4 hydrogen atoms to become 1 helium atom. 600 million tons of hydrogen are converted into 595 million tons of helium every second in the Sun's core due to this proton-proton chain reaction, which accounts for most of the energy output from the Sun. 5 million tons of lost weight will be converted into pure energy. Due to this process, 110 billion megatons of energy are released from the solar core every second. A second reaction sequence in which 4 hydrogen nuclei eventually led to a single helium nucleus is called the CNO cycle, and accounts for less than 10% of the total solar energy. It contains carbon atoms that are not consumed in the overall process. The details of this CNO cycle are as follows: one hydrogen nucleus is added to one carbon nucleus, and nitrogen is converted into the isotope 13. During the collision of one hydrogen nucleus with this carbon nucleus, heat and gamma rays are released from them. Then, due to the high temperature and very high pressure, the nitrogen 13 isotope is released with heat and a neutrino with a positron. Due to this process, nitrogen 13 isotope is converted to carbon 13 isotope. After that, one hydrogen nucleus is added to the nucleus of the isotope of carbon 13 and a nitrogen atom is formed. During the collision of one hydrogen nucleus with the nucleus of the carbon 13 isotope, heat and gamma rays are released from them. Then one hydrogen nucleus is added to the nucleus of the nitrogen atom and becomes oxygen 15 isotope. In the process of the collision of one hydrogen nucleus with the nucleus of a nitrogen atom, heat and gamma rays are emitted from them. Then, due to the high temperature and very high pressure, a neutrino is released from the composition of the oxygen 15 isotope with heat and a positron, and after this process, the oxygen 15 isotope turns into the nitrogen 15 isotope. Then, one hydrogen nucleus is added to the nucleus of nitrogen 15, and due to this process, heat and a helium nucleus are released from the nitrogen 15 isotope. During the collision of one hydrogen nucleus with the nucleus of nitrogen 15, a helium nucleus is separated from it, nitrogen 15 isotope turns into a carbon atom and everything returns to its original state. The rate of nuclear fusion depends on the density. The fusion rate in the core is, therefore, in a self-correcting equilibrium. A slightly higher fusion rate causes the core to heat up more and expand slightly relative to the weight of the outer layers. This condition lowers the fusion rate and corrects the distortion, and a slightly lower rate causes the core to cool and contract slightly. This process increases the rate of fusion and starts all over again. This condition, in other words, the expansion of the atomic core due to heating and the cooling of the atomic core due to expansion, maintains the balance of the heat of the solar core. If the heat balance was not maintained by this process, the temperature of the Sun's core would not stop increasing, and as a result, the life of the Sun would end very quickly. Yes, humans think they are the most intelligent creatures in existence, and yet, while making countless mistakes, it's amazing how these tiny particles with no thinking ability can act so perfectly and flawlessly.